Hello, everyone. My name is Tom Barrymore, and this is my Chemistry Connections presentation. I chose epinephrine as my topic. You can see a little picture of the Lewis structure there and a vial of the medication off to the left. So just real quick, kind of why I wanted to choose this topic. I've worked in EMS for 15 years, and I'm working towards becoming a different level of provider, and I've used epinephrine all throughout my career, multiple agencies, multiple states. It's on every ambulance in the country and every emergency room in the country. And I have a pretty good understanding of the medication. I've used it in a variety of ways, but I don't understand the chemical compound from that vantage point. So, um, quick introduction to what it is. Simply put, it's adrenaline. So this is something that is naturally occurring within our body, but it could also be synthesized in a lab. And it is what is driving the fight or flight response. That's when you're in like a dangerous situation or something scary or life threatening is happening. Your body has an adrenaline dump where it releases a bunch of epinephrine to help you handle the stressful situation. Um, so this is not an anatomy class, and we'll keep it pretty brief on that topic, but just to have a kind of an understanding of how hormones work so that you understand how epinephrine works within the body. Just understand that epinephrine is a hormone, and hormones travel throughout the bloodstream looking for receptor sites that they match. When they find a receptor site that they match, they then bind to the receptor site, causing a response to that organ or that section of the body, right? So it is epinephrine is produced and secreted in the adrenal gland. If you look at the picture off to the right there, we've got a picture of a kidney with the adrenal gland above it. The little yellow portion is the adrenal gland. So there's two adrenal glands, one above each kidney. And epinephrine is considered an alpha and beta adrenergic agonist of the sympathetic nervous system. That's a fancy way of saying that it causes an increase in heart rate and heart contractility, the force in which your heart contracts. It can cause vasoconstriction, which will increase blood pressure. It will cause bronchodilation, which allows us to breathe easier, bring more oxygen into the body, increases your digestion, as well as blood flow to major muscles, and causes pinpoint pupils, right? Because there's a heightened sense of awareness when we're in that fight or flight mode. So epinephrine as a medication, its effects were first identified in 1894. And when I was researching it, it seemed like some scientists were just genuinely just kind of pulling things out of organs. And they found an adrenal gland and they pulled out the compound, the initial compound of epinephrine that was created within the body. And they just started experimenting with it. And they were able to see that it caused um, these effects within the body and that it could be a really important drug. And so it was used before they began synthesizing it. Medical use began in the early 1900s, but it was first synthesized in 1904. And it has multiple life-saving applications. It's given in every cardiac arrest, anaphylaxis, which is somebody having a severe allergic reaction, any respiratory distress, or anything that would cause low blood pressure or low heart rate. It would be indicated. So here is the structure of epinephrine. You look at the formula, it's C9H13NO3. There was a couple different formulas I found when I was going through my research, but this was the most common one. And you can see there's a picture of the compound. The large white balls are the carbon. So you got the carbon ring there in the center with the carbon tail off to the right. And then you can see the oxygen and hydrogen portions, the hydroxide portion of the molecule is off to the left of the six carbon ring as well as above the right tail, the right side of the compound where the tail is. So it's an amphoteric compound, meaning it contains functional groups that act as both an acid and a base. So it's soluble in high and low pH solutions. It is overall a polar molecule, but the carbon ring and the tail are not polar portions of this molecule. So it's only slightly soluble with water. Um, Hydrogen bonds can be created between multiple molecules of epinephrine or other molecules that are open to hydrogen bonding through the hydroxide portions of the molecule. So there are multiple shapes that are listed. This is a complex molecule, but we'll look at some of the ones that we can identify. So the six carbon ring is actually a trigonal planar. You can see on this image over here, it's actually red and not white anymore, but you can see the ring portion, that's the six carbon ring with the right dots going off to the right, being the red, the tail of carbon tail. So the nitrogen bonded portion, which is the green portion off to the right side of the tail, that's actually a trigonal pyramidal shape. And then the hydroxide groups off to the left, you see the blue dots, those blue balls, those groups are bent shaped. So there is London dispersion forces present in all molecules. So they are present in epinephrine as well. And epinephrine is open to hydrogen bonding between molecules via its OH groups. And so there's covalent bonding throughout the molecule as well. And then there are dipole-dipole forces created by the bonds of the carbon and oxygen and the carbon-nitrogen bonds. So we'll do some quick chemistry calculations. Epinephrine has a half-life of 3 minutes. If 1 milligram is given in cardiac arrest, how much is left in the body after 5 minutes? And so we just take our half-life equation, which we know will be 5 minutes equals 1 milligram times 1/2 raised to the 5/3. And if we run through that, we can see that we get 0.315 milligrams left in the body after about 5 minutes. And why is that important to understanding dosages? Well, because we're going to give 1 milligram every 5 minutes or so in a cardiac arrest, and we're going to do it because it's losing its effectiveness, right? And there's not enough in the body to continue. And if, like we talked about earlier, hormones circulate throughout the entire body and they bind at multiple sites. And so if we're looking for a cardiogenic effect, we want to make sure that there's enough in there to have that effect. Um, so we'll do a quick conversion from an adult dose to a pediatric dose. So the dose for a peds in cardiac arrest is 0.01 milligrams per kilogram with a max of 1 because we don't exceed our adult dose. 1 milligram is in a 10 milliliter solution. So the patient weighs 44 pounds, and you can go ahead and round the kilogram conversion to the whole number just to make it easier. We'll assume 1 kilogram equals 2.205 pounds. So the first thing we need to do is we need to convert into kilograms, right? Because we know the mg per kg dose. So 44 divided by 2.205, that's going to give us 19.95. We'll round that up to 20 pounds or 20 kilograms, sorry. So then we want to know our dose is 0.01 milligrams times 20, which is 0.2. So now that we know that the dose is 0.2, we want to find out how many milliliters are we going to give. So if we look at that, our dose in milliliters equals our dose in milligrams divided by the concentration. If you walk through that equation, we'll see 2 milliliters is the solution. And that makes sense, right? If you divide 1 divided by 10, it's 0.1. So if we're trying to give 0.2, we're trying to give 2 milliliters, right? Some quick additional conversions we'll run through. You have a 30 milliliter vial with 30 milligrams of epi used to make epinephrine dripped in cardiac arrest. So let's calculate the amount of moles in that 30 milliliter vial. So first we need to convert into grams, right? Because we know our moles equation requires grams. So we're going to convert 30 milligrams divided by 1,000 equals 0.03. So then from there, we need the molar mass. I went ahead and just calculated the molar mass. The molar mass is 183.2. So take 183.2. You're going to take the 0.03 divided by 183.2 to get our number of moles, which is 0.0016375, or we could put that in scientific notation. It'd be what, 1.64 times 10 to the negative fourth. And then the last conversion we'll do here is we have 1.64 times 10 to the negative 6 moles in an EpiPen. What is the dose in milligrams? So we got our equation here. It's the same equation, we're just rearranging it, right? So in order to get grams, we're going to take your moles times your molar mass. So we take the moles times the molar mass. That gives us the amount in grams, but we want to get it in milligrams, so we got to times that by 1,000, which gives us 0.3. And the adult dose for an EpiPen is 0.3 milligrams. So that is correct. There are some of my sources. I appreciate you guys listening and giving me your ear for about 10 minutes. I hope it was beneficial in some way, and I wish you all nothing but the best on the final. Thank you.